So we're going to look at binomial probability. We're basically going to, it's an application of the binomial theorem we've been looking at. We're going to apply it to probability. And if we think of it in a very simplistic point of view, all probabilities, there's only one of two things happen. Either it happens or it doesn't happen. So we could break anything down to it happens or it doesn't happen. So if there's two possibilities and the event is repeated, what happens? Well, if I only do it once, it could either be A or B. And the naive person would say there's a 50-50 chance, but in reality we know that's not always the case. Let's say A has a probability of P, B has a probability of Q. P and Q, of course, would add up to 1. Okay. And then we do it a second time. The A branches off, we now have AA, AB, BA or BB. So the probability of AA would be P squared, then AB, PQ, BA, PQ, BB, Q squared. Then we'll do it again. Whoop. Branch off, AAA, AAB, ABA, ABB, the sheep probability, BAB, BBA, and BBB. Probabilities, P cubed, P squared Q, P squared Q, PQ squared, P squared Q, PQ squared, PQ squared, P cubed. Oh, what the heck, let's do it again. And we go AA, AAB, AAB, AABB, baby, AAB, a band from the 70s, ABBB, AAB, and the very last one, of course, just a silly person when you think about it. Okay. Now, probabilities, P to the power of 4, PQQ, and so on, and so on, and so on. And all these things possibly are looking familiar if we look at it differently. So when there was one event, probability of A was P, probability of B was Q. Okay. Two events, probability of AA. But if I don't care about the order, remember probability of AB was PQ, but so was BA. We get 2PQ, but look at those. P squared, 2PQ, Q squared. If we look at three events, P cubed, 3P squared cubed, 3PQ squared, Q cubed. If we look at four events, P to the 4, 4P, they're exactly the same as the expansion of our binomial. Now, it's not a coincidence, because what we're really doing is we're saying all the possible outcomes are P and Q. So we're saying P plus Q equals 1. In each parenthesis, we've got P plus Q. If there's four events, we're going first event, either P or Q. Second event, either P or Q. Third event, either P or Q. Fourth event, either P or Q. So if I want A to happen 3 times, B to happen once, I'm saying out of those 3 parentheses, I want to pull P out 3 times. Well, that's exactly what we did when we were working out the coefficients of the binomial. So binomial probability is really just the general term of the binomial theorem. So if an event happens n times, we know the probability of it happening is P, probability of it not happening is Q. And we want the event to happen exactly K times. There it is, NCK, probability of it happening to the power of K, probability of it not happening to the power of n minus K. Exactly the same as our general term in the binomial theorem. My notation when I do it is I say probability x equals k. It simply means that event x is going to happen exactly k times. So let's look at an example. Oh, by the way, this has to be with repetition, of course, because the probability has to be the same every single time. So if in a question like this we didn't replace the balls, the probability would change. And so we couldn't use this idea. We'd have to go back to, the counting principle or perms and coms, that sort of thing. So all black balls, well, we don't really need it for this, but just to illustrate that it would work. Because obviously if they're all black, we'd just say probability of black, well, it's going to be black each time, so 3/5, 3/5, 3/5. But what I'm saying here is X is representing the number of black balls. If it's going to be 7, so it'll be 7C7, which is of course 1. The probability of it happening to the power of 7. The probability of it not happening to the power of 0, which again is just equal to 1. And so yeah, we get that 3/5 to the power of 7. That's it, unsimplified. This one we can probably simplify. That's not too big a number. But a lot of times with these binomial ones, we'll leave them unsimplified because the numbers can get quite large. All right, well, what happens if I only want 4 black balls? Okay, well, now I'll do x equals 4. Sub it into that general term. 7c4, probability of it happening to the power of 4, probability of it not happening to the power of 3. There it is unsimplified. That one simplifies down to be 4,536 on 15,625. You probably guessed that anyway. Maybe. All right, an election. 30% of voters favour Party A. What's the probability if we selected 5 people? What's the chance that 3 of them favoured Party A? So X is going to be the number representing Party A. So I want 3 A's or X equals 3. I don't know why I wrote 3A there. It's written X equals 3. But anyway, 5C3, probability of happening to the power of 3, probability of not happening to the power of 2. There it is unsimplified. Mind you, for a question like this, we probably want an actual answer. And in reality, I'd probably change it to a percentage. But what's that as a percentage? 1323 over 10,000. 13.23%? Okay, 13% chance, 13 and a quarter. Majority favour A. Well, that means either 3, 4 or 5. So we just work each of them out and add them together. So it's the same as our basic probability theory that we've seen before. This one calculates to be this beautiful expression, which is 4,077 out of 25,000. At most 2 favoured A. Again, don't forget your basic probability ideas. We've just worked out the majority favour A, 3, 4, 5. So if at most 2 favour A, that must be the complementary event. So I'm not going to waste time. I'm going to say, hang on, well, that's just 1 minus what I've already worked out. So subtract from 1 and we get our answer. So obviously all our probability theory from before, it still works. Let's have a look at an HSC one. So from 2005, 5 matches each weekend of a footy season. Megan takes part in the competition. She gets 1 point if she picks more than half of the winning teams for a weekend. 0 otherwise. It's a very strange tipping competition, this one, but all right. The probability that Megan correctly picks a team is 2/3. Show the probability she earns a point is 0.7901. So in order to earn a point, what's she got to do? Where is it? 5 matches, pick more than half. Okay, so X is going to be the number of matches she picks correctly. We want X greater than or equal to 3. She's either going to pick 3 teams right, 4 teams right, or 5 teams right. So each of those, 5C, well, the first one, 3, probability of it happening to the power of 3, probability of it not happening, power of 2, and so on. So add up each of these, bung that into our calculator, because we want to show it's close to 7901, and yes, indeed, that is 0.7901. We now want to work out the probability that Megan earns 1 point every week of the 18-week season. So now we're going to say, let Y be the number of weeks she earns that point. So we want to know, when is Y equal to 18? She's going to get 1 every single week. But remember, we just worked out the probability of her getting a point is 0.7901. So we don't use the probability from the last one. We're using the probability we just calculated. And, well, I've done it using binomial probability. So 18C18. 0.7901 to the power of 18, and it comes up to be, to 2 decimal places, 0.01. We want to know she earns at most 16 points during the 18-week season. So at most 16. I'm going to use the complementary idea because I don't want to work out no weeks, 1 week, 2 weeks, 3 weeks, 4 weeks, 5 weeks, and add them all together. It's going to be easier to work out 17 or 18, especially since we've already worked out 18. So it'll be 1 minus 17 weeks minus 18 weeks. Again, chuck that all into our calculator. It will end up with 0.92 to 2 decimal places. Have a look at another one from 2007. A large city, 10% of the population has green eyes. Obviously not our city. Okay. What's the probability that 2 randomly chosen people have green eyes? So probability of 2 being green is simply going to be, well, 0.1 times 0.1, 0.01. They've both got to have a 10% chance. So that's not binomial probability, the first bit. The second bit is, however, probability exactly 2 of the group of 20 randomly picked people have green eyes. So I'm going to say, well, X is going to be the number of people with green eyes. We want probability that X equals 2 out of those 20. So 20C2, probability of it happening to the power of 2, probability of it not happening, power of 18. So we have 0.285. Most of these binomial probability questions are fairly straightforward. It just is a matter of remembering, hey, it's exactly the same as the general term of the binomial, and just sub the data in. What's the probability that more than 2 the group of 20? So more than the group of 20. So we're saying X is greater than 2. Once again, I'm not going to work out 2, 3, 4, 5, 6. Easier to work out less than or equal to 2 and subtract. So there's only 3 things I have to work out there. So 2, 1, and 0. And we get 0.32. Alrighty. So 10J is that exercise way back last year when we did perms and coms. And we didn't do 10J because 10J was on binomial probability. We can now go back and finish that chapter